Okay, my friends, here we go again for 4.5. And this is on the substitution. And so the unchained rule, as I like to call it. And so let's get on our paper review and let's check this out. Am I recording? Yes, 20 seconds worth so far. Oh, I don't want to stream. Sorry, council. Did I do that wrong? Paper review is what I wanted. Hopefully you're still going. Am I still recording? Yes. Okay, 4.5, the unchained rule. And so what we did, as you remember in chapter 3, we were finding the derivative using the chain rule. So if we had to find the derivative using the chain rule, the outside function here would be the outside function would be 1/20 raised to the 5th, right? And the inside function would be 2x squared plus 3. So that if we were going to take the derivative of this, so we are finding the derivative, not finding the integral, so something different, something that we haven't done since chapter 3. I mean, that's just a little while ago. And so we would use the power rule. 5 times 1/20 is 1/4. Raised to the 4th, the same inside, right? So 5 times 1/20 is 1/4. Raised to the 4th, you take away 1. Remember, when you're taking the derivative, you take away 1 from the exponent, times the derivative of the inside. And the inside, that would be 4x plus 3. So the derivative of the inside is just 4x. And remember, evaluated at the same inside, which was 2x squared plus 3. That was the derivative of this part right here. And then the derivative of 19 is 0, so plus 0. And so when I put this together, 1/4 times 4x is just x. So the derivative is x times 2x squared plus 3, 4. Plus 0, right? And so now they're asking us, hey, if we could find the antiderivative of that. And so just by our thoughts that hey, they're inverses of one another. I mean, notice this, right? And so the antiderivative would be just what we started with here. But what about the 19? What do y'all think? Yeah, we have no way of knowing what that number was, right? That number could have been 20 or could have been 57. And when we took the derivative of it, we would have got 0. And so we have no way of knowing. That's why the plus C, right? And so we had no way of knowing if it was 19 when we get back what we started with. And so this is definitely would be the answer by the fundamental theorem of calculus, but how could we find that answer? I mean, that's what the fundamental theorem of calculus said, that that if you take the derivative of this and you get that, right? And so, but how do we go from here to here? And so we know because of the chain rule how to go one way, but now we need to learn how to go the other way. And it's called the unchained rule. And I call it the unchained rule, but the book calls it the substitution rule, and it doesn't matter what you call it. But you are definitely going backwards. And so, and I want you to also notice that this was a product, but it was a special product. So we are going to learn how to find the derivative of a special product in Calc 1, and you'll learn to find the derivative of any product in Calc 2. So just a special product here in Calc 1, and we can't find them all using this method, but we'll be able to find a lot of them using this method, and then in Calc 2 you'll learn how to find more, and etc. Okay, so that special product comes when you have this situation, when you have a function with an inside multiplied by the derivative. That's what your input in your argument or your integrand, whatever you want to call it, into your antiderivative. And so when when you have that special situation. And then they say that the answer would be the integral. Now they call that inside function u, is what they call that inside function. And g at x, they call that u. So they say that that would be the same as the integral of f of u du, because they're calling that inside function u. And so anyway, so that's kind of that situation. And if you have bounds, it would be the same thing, but there would be bounds on them, and you would want to change those bounds into your u substitution function. And so we're going to give a try to, that, I mean, this theorem is lovely, and it just basically says that, hey, if what you've got came from the chain rule, then you'll be able to find the antiderivative. But they introduce this u thing, and you're like, what the heck? And so this is actually the function notation that Euler, originally, he was German, came up with, not f at x, but f at u, which is funny for Americans. And anyway, but maybe not for everyone. Okay, so what you do, this is the procedure, the how-to step by step, and then after you've done it a few times, you're not hanging on the procedure, but this is our first time going through it, so we've been kind of hanging on the procedure. You let u be g of x, and that's some inside function. Then you differentiate u, and you put this in differential form. If you're not remembering differential form, we learned about it in the same chapter that the mean value theorem was in, whatever chapter that was. It was chapter 3, but whatever section that was. And then I like to solve for dx, and this is how I learned to do it anyway. And so it's helpful when you first learn, and that's what I was taught to do, so that's what I like to do. And then substitute u and dx. Hopefully you end up with an equation with only u's in it, and if you don't, then you have to make it so. And so you can't have x's and u's, and so you're basically going to be substituting in, and then hopefully that you've now created something with u's that is something that you can integrate. And so you integrate. If you haven't created something you can integrate, then you might be at the drawing board again trying something else. And then bounds versus no bounds versus bounds. If there's no bounds, then after you integrate, you have to go back to x and don't forget your plus c. And I like to put plus c on my answer line so I don't forget it. And there's two options if you have bounds, and that is to change the bounds into u as well and never go back to x. That's a bad joke about I'm only into u, but I'm not going to go back to my x, that kind of joke. Or you can go back to x's and change the bounds back to x's, and then evaluate those bounds. So either way on that, it's actually easier. I like to change my bounds into u and then never go back to x is what I like to do. Okay, and you'll see that. So this problem right here, of course, is it the same one we started with, or is it just really similar? Let me go look. It's just really similar. Oh no, it's the same one we started with. What am I saying? Okay, we already know the answer to this, right? It's the same one we just did, so we already know the answer to it, but we're going to make sure that we can get that answer. And so how do you check your answer? By find the derivative, and of course we've already done that. Okay, so what you want to do first step, is let u equal some inside function. And so in this case, and I like to, a lot of times I write it as my plan. This is my plan for taking the integral of this. I can't integral this because I can't find the integral of this because it's a product. And you cannot find the integral of the product of the pieces. So you can't find the integral of each piece and then multiply them together. So my plan is to let u equal the inside function. And so the inside function is right here, being raised to the fourth. So 2x squared plus 3. Then what you do is you write this in differential form. You take the derivative. So you don't write du dx like that. That's not differential form, which was equal to 4x, right? When you write it in differential form, instead of writing it du dx like that, you write du equals 4x dx. Y'all remember that? And so instead of writing the derivative as du dx, you write du equals 4x times dx. And then I like to put a box around this. Of course, I'm a very boxy person. And then I like to solve for dx. So I like to write du divided by 4x equals dx. And this is particularly helpful when you first start. And I put a box around that. Okay. And then now I'm going to implement my plan. So this is going to equal the integral. And I'm going to write here, I'm going to substitute in where I see 2x squared plus 3, I'm going to substitute in u. And where I see dx, I'm going to substitute in du over 4x. So right here are my two places I'm going to substitute. Now this value right here, I'm not substituting anything, but I'm hoping it will cancel out with what I have. And if it doesn't cancel out with what I have, then I either have to try to make it so or do a different method. And then I'll know I'm in Calc 2 when I'm having to do a different method. Okay, so this is x times u to the fourth, because remember I was going to replace this with u. And then dx is du divided by 4x. And I'm hoping that the x's will cancel out. If they don't cancel out, then I'm like, shoot, what can I do? Because I got to try to make that happen. But on this case, they cancel out, right? The x's are gone. I have x divided by x, that's 0. I have this 4 in the denominator. And so I can put that 4 out in front if I like. That's 1/4. I can put it inside the integral or on the other side of the integral. My choice, it doesn't matter. And so I have to admit that I do put it on the outside. So this is going to be 1/4. The x's are going to cross out. So I'm like hot diggity dog. And then u to the fourth du. And if this is not something you can integrate, then you have to try harder. But hey, that is something I can integrate, right? I know the integral of u to the fourth du. That's u to the fifth, right? Over 5. So the 1/4 holds still times u to the fifth over 5 plus c, of course. And probably I should just put plus c when it doesn't have bounds so I don't forget them. So that's 1/20. And then u to the fifth, but remember u was equal to 2x squared plus 3. 2x squared plus 3 raised to the fifth plus c. And you notice that's the same answer that we got before, right? So how do you check your answer? Well, you can find the derivative of this and show that it's equal to that. So that's how you would check your answer. I don't know why I put that so high up and not just kind of at the bottom. And so maybe so that I can write, find the derivative of 1/20, 2x squared plus 3 raised to the fifth plus c, and show equal to the x times 2x squared plus 3 raised to the fourth. So yeah, so maybe that's where I was wanting. I don't know at the time. You know how you go. Okay, so we did a lovely job on that one. And so that's the step-by-step. That was an example without bounds, and we have the plus c, and we had to make sure that we go back to x, right? So we had to return back to x's. And that was actually number 2 out of your textbook on 4.5. This is problem 19 out of your textbook. 19 is my favorite number, so it only makes sense that I would choose number 19. Okay, so cosine cubed times sine d theta. And so that notation written that way makes it hard sometimes to find the inside function. That is a product, though, right there. And it's not one of my 6 basic trigs, right? So I can go and look, and I don't have any on the basic trigs that are cosine cubed times sine. And so, you can go back to your trigs that we learned in the previous section, chapter 4.4, right here. And you can say, here's my 6 things that I know. Is the thing I have exactly one of those 6? And the answer is no, it's not one of those 6. So because this is written so awkwardly, I think it's awkward anyway, I would rewrite it like this. Cosine theta raised to the third multiplied by sine theta d theta. And then now our idea is, if you have a product that you don't know how to handle because we don't know how to do a product, our plan can be to do a U substitution. And how you do a U substitution plan, and it's the unchain rule is what it is. Does this always work? And the answer is, if it's set up to work, it'll work. And if it's not, it's just something to try. And then there's other things that we can try as well, and we'll learn those things in Calc 2. And so if you're like, now the other thing that we had with trig is to use a trig substitution. So that would have been another thing that I could have done on this. And so I'd forgotten to mention that because I got so excited because I was in the U substitution section. But in the previous section, what we tried to do was a trig substitution. Well, I'm not sure that a trig substitution would work on this. I do know what cosine squared is, but it's something so nasty, right? And I got cosine cubed here. But watch this U substitution. It's going to work quite slick. You let it be the inside function. U equals cosine of theta. Then you have to take, in this case, it's du d theta. The derivative, you're finding the derivative, but you're not going to write du d theta because you're going to write the d theta on the other side. So you're going to write du equals, y'all know the derivative of cosine? Not the integral of cosine, the derivative of cosine. It's negative sine d theta. Then I was taught to solve for d theta. So this would be du divided by negative sine of theta equals d theta. And I was taught to put a box around u and a box around d theta. And then we're going to go plug it in, is what we're going to do. Right here, we're going to plug in u, because this is our plan. And then right here, du, for d theta, we're going to put in du divided by negative sine of theta. And we're hoping that sine of theta will cancel out, is what we're hoping. If it doesn't cancel out, then we have to do something different to make it so that it does cancel out. But in this case, it is going to cancel out. It's going to cancel out with the d theta. So it's like hot diggity dog. And so, so this is going to be the integral. Remember, we're going to replace that with u to the third, times, and I'm going to write sine theta right now because I know it's going to cancel, times, and then this is du divided by negative sine of theta. And so the sine of thetas cancel out, leaving this extra negative, and you can put that negative out in the front. So this would be negative of the integral of u to the third du. And it's like, well, I know how to find that. It's an easy integral to find, right? That's u to the fourth over 4. So this is negative u to the fourth over 4 and plus c. And then remember what u was. It was cosine theta. So this is negative of cosine theta raised to the fourth over 4 plus c. And of course, I don't care if you go back to that notation of putting the 4 right there on the s. I mean, that's okay. So this is great, perfect, wonderful, I'll say, wonderful. And this, I hate to say this is wonderful too, because I hate that notation. But I want everyone to know that they're just the same. So I guess I'll say it's wonderful as well. Okay, so that's kind of our story there. If I wanted to check my answer to make sure that my answer was true, then what I would do is I would take the derivative of that, or that, whichever one, they're the same, and show that I get that right there. That's what I would do. And so I would be having to use the chain rule in order to find the derivative because it has an outside function. The outside function is actually negative of the parentheses raised to the fourth over 4. You could put that as 1/4. And then when you take the derivative, 4 times 1/4 wipes it out. And then you have to take the derivative of the inside, which is the sine, get the sine. And of course, the negatives are going to boil out too on you. And so you're going to be in good shape. So that was that story. So we did a lovely job on that. Here they're asking us to find, instead of a indefinite integral, they're asking us to find a definite integral, meaning it has bounds and that means that it would mean area under the curve. And the area under the curve from 0 to the square root of pi. And so we're going to give a try to that. So how you find the area under the curve on a definite integral is you find the antiderivative. So when I go looking to find the antiderivative, it's x multiplied by cosine x squared, and that's a product. And if I go here to the trig integrals that I know, I have them here. Right here, I notice that none of them start off with x times cosine of x squared. None of them look like that. So what I have to do is, because I have that product, I'm hoping that that product came from a chain rule. And if it didn't come from a chain rule, then this won't work out when I go to do it. And if that happens to you ever, you'll know that you're in Calc 2, because we have another way of finding the derivative of products that don't come from a u substitution. And so that's what we're going to try now. So in Calc 2, you'll try the u substitution and you'll say, darn, it doesn't work. Let me use the product rule. And that's what it's called, the product rule. And so anyway, so what I want to do is this is my plan. I want to let u be my inside function. So I'm kind of looking at that and I'm thinking, what is the inside function there? And I hope that you're saying that it's x squared. And if you are saying it's x squared, if you're right. And if you're not saying it's x squared, you can try what you think it is and see that it doesn't work out. And so then I want to find the derivative. So I want to write that du dx, but remember I want to write it in differential form, which means to put the dx on the other side of the equation. That looks like a y, sorry. And so this is going to look like du equals 2x dx. Du? What? And then I was taught to put a box around u, and I was taught to solve for dx, du divided by 2x. You get where after a while, even though this is how I was taught to do it, that I learned a different way myself, or even saw videos different way than that myself, and that's fine too. And so, but I think it's kind of nice. When I have bounds, I like to make a plan with my bounds as well. So here's my bounds, and these bounds are for x. This bound says, this is the lower bound, says x equals 0. But I know that u equals x squared. So u equals x squared, I'm going to plug in 0. U equals 0 squared, u equals 0. Yeah, it's a coincidence that it's the same. But the up bound, that bound is x equals the square root of pi, not x, pi. And u equals x squared, u equals the square root of pi squared, u equals pi. So our low bound will be 0 for u, and our up bound will be u equals pi. So everything will be in terms of u here in a second. So my bounds, I know they're going to go 0 for u to pi, right? And those bounds are in terms of u. This is u. This is u. That x right there is not what I was substituting. That's the x I'm hoping will cancel out. Here's where I'm substituting. So that's cosine of u. That's x squared. And then dx, remember, was du over 2x. If those x's, if that x right there doesn't get canceled out, then I'm going to have to do something different. I'm going to have to figure out something else. I might have to, well, don't worry, there's going to be some that are just a tiny bit trickier. I call them a double sub. And anyway, but it does cancel out. So I'm like, hot diggity dog. So this is going to be then the integral of 0 to pi of cosine of u du, and I had this half, right? That's over 2. And so I'm going to put the half right out in front. I forgot to do that. And then when I got there, I was like, ooh, I forgot my half there. And then now I'm going to find the antiderivative. And I know the antiderivative of cosine, any variable, it doesn't matter, right? Remember, that was one of the first lessons that they told us, is the integral of cosine of u du is equal to the integral of cosine of x dx, right? They told us that we can change the variable to be whatever variable that we want. It would be equal, and you could use theta instead, whatever you want. And that was equal to, y'all remember what the integral of cosine of x dx is? It's one of our memory verses. Y'all remember? So the half, I hope that you're saying sine, right? Sine of u, because this is the variable u, so I'm going to keep the same variable. And then these are bounds are for u as well. This is u goes from 0 to pi. So it's okay for me to plug in for u. Now, I would not want to change these bounds back into x. I wouldn't want to go here and say, well, u equals x squared, because if I did that, then I would need to change my bounds back to x as well, which would be 0 to the square root of pi. And so right now, it would be much easier, instead of having x squared here and 0 to the square root of pi, just to have u and 0 to pi. But they're equivalent to one another. So this is the up bound, 1/2 sine of pi, minus the low bound, 1/2 sine of 0. This must be, that's 0, isn't it? Sine of pi is 0, and sine of 0 for sure is 0. And so this is equal to 0. I'm like, what? Can that happen? Can an integral be equal to 0 and it's supposed to be area? And the answer is yes, it could, because it's not just area, it's net area. I wish I had a way of putting the graph on the Desmos. I have a way of showing my MacBook screen, but I forgot to ask Tyler to update that for me, because every time I unplug my computer, that link has to be reestablished. Maybe one of you can help me with that, why I have to do that. Anyway, so I can't show you my screen to graph this, but you can go graph this from 0 to the square root of pi, and there must be the same amount of area above the x-axis as below the x-axis, and therefore the answer is 0. And so it makes me want to have to do that right after this, and so that before I even upload this to YouTube, make sure. Okay, so this one right here, it's a division instead of a product, and so we're going to be able to maybe do it the same way, and so we're going to give it a whirl and see how we do. And so you cannot find the integral of a division except for by making some kind of a plan. And so you can find the integral of an addition or subtraction, but not of a division. And this one has bounds too, so it's a definite integral. So I'm going to let u try to be an inside function. So I'm going to try to let u equal like 1 plus 2x. That would be inside of the square root. And then remember, you do the derivative, which is du dx, but I want to write it in differential form, which means I write it du equals, well, the derivative of 1 is 0 and of 2x is 2, so dx, but instead you write it like this. Instead of du dx, you write du equals 2x. And then I was taught to solve for dx, so that would be du over 2 equals dx. And I'm already saying, that x needed to cancel out. I'm going to substitute this all in for u, so it's going to be gone. And then when I put in du over 2 for dx, I was hoping that that x up there would cancel. And I'm like, it's not canceling. And so, I'm here scratching my head. If you can see me scratching my head here, ooh, what am I going to do? And remember, I was taught to put a box around this. And I was taught to put a box around that. And so I can't help but want to do the same thing. I can take this and I can solve that for x. And if I do, it looks like u minus 1 equals 2x. And then it looks like u minus 1 over 2 equals x. So this right now is something I cannot find the derivative of. But now I have something that I can put in for that x that only has u. So I actually, and that's why my son calls it a double sub, is because I'm going to be subbing in this and this, which is my normal substitutions, but then I'm not going to get rid of x, as you can see, and so I'm going to substitute in this, which will get rid of x altogether. And then I have bounds. So the low bound look like x equals 0, and so the up bound, so u equals 1 plus 2x, right? So that's u equals 1 plus 2 times 0. So that's u equals 1. So that will be the new low bound. U is 1. And then the up bound is x is 4. U equals 1 plus 2x, which is 1 plus 2 times 4, which is 9. So the new up bound is 9 for u. So I'm going to convert everything in to u. So here, when I start doing this, the new bounds for u are the low bound is 0. Oh, no, it's not. It's 1. Sorry. I need to circle that so I remember. And the up bound is 9. And then I'm going to be substituting in x over the square root of u, and then du over 2. And the reason that I went and found out what this u was, what x was in terms of u, is because it wasn't going to cancel. And remember, I'm supposed to get rid of all of it. Now, luckily on other problems, right down here canceled with that. But that's not happening here, and that's the reason I went and found that that u minus 1 divided by 2 equals x. So I'm now going to put that in for that x right there. I'm going to write it right here. So this is going to be integral from 1 to 9, and then I'm going to have the square root of x in the denominator, and then I'm going to have u minus 1 over 2 up there in the numerator, and then du over 2. And that part right there, I guess, was the calculus part, but simplifying that right there is going to be the I don't know, beginning algebra part. And that's going to be the hardest part of the problem. I mean, I don't know if I'm going to call this calculus, but I'll give you that this is calculus. I'm going to definitely give you that this step from here to here is calculus, right? But most of this is algebra, and so this is something I would not been able to simplify in order to find the integral of it when I was just a wee girl. And so this right here is 1/2 is what it is, because it's you could write that out in front if you wanted. So here I've written it as u minus 1 over 2. If I wanted to, I could have written it as 1/2 of u minus 1. And then what I could do with that 1/2 is I can put that 1/2 out in the front. And so I just wrote it the way I normally would write it so that I could show you that, hey, if I wrote it like this, maybe you would have been happier with it, because then it's really clear that that 1/2 can go out in the front. And then we've been putting this out in the front as well. And I hope that you remember that that would go out in the front as 1/2 as well. So how this is going to look then is 1/2 out in front, another 1/2 out in front. Coincidentally, they're the same. And then quack, quack, quack. The integral 1 to 9 of u minus 1, because I put that 1/2 out in front, and divided by the square root of u du. And of course, 1/2 times 1/2 is 1/4. And I hope that you're looking at this and saying, well, it's a division. I cannot divide that. But wait a minute. it's a division, but you can divide that. This was a division that I couldn't divide. After I did my U substitution, I turned it into a division that I can divide. And so I'll be able to divide it and then use the power rule. And so, so here we go. We're going to have 1/4. The bounds are 1 to 9, and those bounds are for U. And then this is what I'm going to have here. U over the square root of U minus 1 over the square root of U. I normally would think that. And this is 1, and that's 1/2. So this would be U to the 1/2 minus, what would that be? I hope you know. I know, I'm asleep too. I'm feeling like I should be in there watching the Angels game, but they were losing. And so I said to Tyler, I said I would make 2 videos today. I got to go make that other video as long as these losers are losing. And I told him, come get me if they start scoring, and then I'll just stop the video at that point. So you know the Angels aren't scoring, and that's why I'm still in here. Okay, so now I'm going to add 1 and divide by the same darn thing, right? So I have U to the 1/2, and then when I add 1, that's going to be 3/2, right? And I'm going to divide by the same darn thing. So I am going to find the integral, and I'm going to put a box here so that I say to myself the 1/4 is times all of this stuff. So this is U to the 3/2, and divide by 3/2, which is same as timesing by 2/3, and then minus, and then add 1. So negative 1/2 plus 1 is 1/2. So that's U to the 1/2. Then divide by 1/2, which is the same as timesing by 2. And then my bounds go from, where did they go from? 1 to 9. So now I'm going to do up bound minus low bound, and I'm really grateful that those bounds are really nice, because 9 to the 3/2 is a nice number. 1 to the 3/2 is a nice number. 9 to the 1/2 is a nice number. 1 to the 1/2 is a nice number. And so this is going to be 1/4. And then this whole thing, it's going to be, this is my up bound minus my low bound. And so this is, I gave a lot of room for that bound, but maybe not as much for that bound. So this is 2/3, 9 to the 3/2, minus 2 times 9 to the 1/2. And then in here, I'm going to make it a little bit bigger. I'm going to have 1. But it's nice because 1 to the any power is 1. And so 2, and then I missed my power because I said that it didn't matter if I put it, did I? Is that what I said? Okay, so my plan is to put that in my calculator, get the answer, put this in my calculator by editing this, because they should be the same, and with ones, and then subtract them and multiply by 1/4, and be happy, or Hoppy. That's Hoppy is one of the Angel players. Do you guys watch Angel baseball? Mr. Greenwood will only give extra credit if his team wins on things. So there's no extra credit unless his team wins. It's like he bets the class with the extra credit. It's kind of weird. I might be wrong on that, but I heard rumors. So I'm typing this away into my calculator. Okay, so I got that put in the calculator with the 9s, 2/3 times 9 to the 3/2 minus 2 times 9 to the 1/2, and 12. I expected to get a nice answer. So this is 1/4, and then this is 12 minus, and then I'm going to go substitute those 9s for 1s. If I didn't have it, or that's already typed, I could just put it in again, because it's really just 2/3 minus 2 is what it really is, because 1 raised to these powers is nothing, which is negative 4/3. So this altogether, when I put this in my calculator, is going to be 12 plus 4/3, which is 40 over 3. and then times 1/4, or divided by 4. So I'll divide by 4. So this is 10 thirds. The main step that you want to show so that you can make sure that you get credit for knowing the fundamental theorem of calculus part 2 is putting in the 9s and the 1s right here. This part right here, if you just put the answer, got the answer 10 thirds with your calculator, I would have been totally fine with that. And so, but if you want I know that people can plug this in their calculator and get the answer without writing this. And but if you want part credit, if you mess up, and I'll tell you that more mistakes happen right here than any other place. I'll just tell you that. Just be honest with you on that. If you want part credit, the credit for knowing the fundamental theorem of calculus, you have to show this. Otherwise, I don't know if I don't know what you were plugging in. I just know you have the wrong answer. And so anyway, you always have to show your antiderivative going along because this silly calculator will find the integral right here. There's the integral button right there on it. And I'm not interested in whether or not you know that how to use your calculator. I mean, certainly you can use it to check. I shouldn't even show you, but that's the kind of nice person I am here. And I need to get over there and get in that box. There, I was in it. Okay, and I want fraction, and I want x, and then I want downstairs square root of x, 1 plus 2x. And, oh, I put 20. Why did I do that? I don't know. Okay, so I have 0 to 4, that, and I hit equals, and it comes back because it estimates it. So 3 and 0.33333, that's 3 1/3 is what that is, and that's what 10 thirds is, 3 1/3. So, of course, we want the exact answer. This answer right here is an approximated answer. This is the exact answer. We're math people. We want the exact answer. Okay, so this is number 14 in your book. And it's in the you need to use a U substitution situation. But really, I don't need to use a U substitution on this one because I have memorized. Gosh, who is just texting me away? It's just crazy. It's my dad telling me, don't forget about the eclipse on Monday. And so, yeah, that's necessary to know because I got a plan for what time is it. I don't even know if you're going to be able to see it in Bakersfield. But right here, right, this is on the second page of your notes, that if you have secant squared a of x equals, that's tangent a of x over a. So actually, this is how I have it memorized. Secant squared ax dx equals tangent ax over a plus c. That's how I have it memorized. So I don't have to do a U substitution or anything like that on this one because, and what they were hoping for, if you didn't have your thing memorized like this, is that you would let U equal to theta and then blah, blah, blah. And you would get the same answer that I'm going to get right here. But on this one, because of the way I have mine memorized, this is going to be tangent of 2 theta over 2 plus c. So I don't have to do a U substitution if this is the way I have it memorized. If I don't have it memorized that way, then I would be going U equals 2 theta. Du equals 2 d theta. Du over 2 equals d theta. Box, box. There's my plan, right? So that secant squared 2 theta d theta equals, so for 2 theta, I'm going to put in u, the integral of secant squared u, and then du over 2 equals d theta, so that the half comes out in front, and the integral of secant squared u du. And then for sure you have that one memorized. So if you haven't memorized it like this, then you have it memorized like this. It's all good. I mean, whichever way you like best, right? And so then this would be 1/2 times tangent the variable instead is u, not x. So this is u, and then plus c. And then you would need to go back to from u's, right? And u is 2 theta. So this is 1/2 tangent of 2 theta plus c. And you notice that using the u substitution, we get to the same answer. So it's on you on whether or not you've memorized them like this. This is what I was taught to do. It's not what our book does. I didn't learn out of the Stewart book. I learned out of the Thomas book. There's 2 main calculus books. Both authors are actually passed away years and years ago, Stewart and Thomas. And so when I learned at Bakersfield, I took Calculus 1 at Bakersfield College. We were using the Thomas book. I sometimes vote for the Thomas book. I never vote for the Stewart book, but it's a good book too. And I told you one time that the author made $30 million worth of improvements on the house that he bought at Niagara Falls. And I don't even know when that was. I don't know how long he's been passed away, but maybe he's passed away 10 years ago, so it's a long time ago. Okay, this is a division. And so I'm kind of thinking, okay, if it's a division and if I can't simplify it, that I could use a u substitution. And actually, you can simplify this because secant squared is 1 over cosine squared, and sine squared divided by cosine squared is equal to tangent squared. So I could do a trig substitution, and so this would be a trig sub. Now when you do a trig sub, you're not changing your variables because you're just saying things that are true with your trig. So this would look like the integral secant is 1 over cosine squared x, tangent sine squared x, because they're squared, over cosine squared x, and so dx, and the cosines squareds cancel out. I don't know, calculate out what that means. So this is 1 over sine squared x dx. And well, that's not one I know, but I know on my trig that is equal to cosecant squared, right? And then I'm like, oh, that is one I know. So this is me finding this integral using a trig substitution. And so that could be a way that you did this integral. And that is equal to, and so I'm looking back here. I don't want to get the sign wrong because I've been celebrating baseball here. Well, I wasn't celebrating baseball unless I'm rooting for that other team. I don't even know who they were playing today, but it was bad. So the cosecant squared x dx equals negative cotangent x plus c. So this equals negative cotangent x plus c. Okay, that would have been a way of doing this problem using a trig substitution. I want to show you the way of doing a u substitution, and they would both be right. And so it would be a decision you make. So you could have done a u substitution by rewriting this with tangent of x squared like that dx. Now, if you're thinking, well, why did you do that to the tangent and not to the secant? It's just because I've practiced my derivative so much that I know the derivative of tangent is secant squared. And so if I let my u be tangent of x, then when I do my du, I get secant squared of x dx, and it gobbles it up. And so you can see it right here, secant squared dx. Now I was taught to solve for the dx, but you can kind of see that those two pieces together make du is what they make. So I'm going to just put a box around that this time. And so this is my plan on my u sub as substitution. And so right here in the numerator, I have the integral, and that secant thing is what I was hoping would get gobbled up. Oh yeah, it does get gobbled up. This part right here is going to be gobbled up, and that whole thing is just du. I guess I like it to cancel it out better. So this part right here gets substituted and just becomes du. If that becomes du, see how that is just du, then what is up there in the numerator? I hope you're saying a 1. And then in the denominator, I have u squared. And then this is then the integral of u to the negative 2 du, because I want to set it up so I can use my power rule. How you use your power rule is you add 1 and divide by the same darn thing. So if I add 1 to negative 2, I get negative 1/2, not negative 1/2. Negative 2 plus 1 is negative 1. That's what I was trying to say. And I'm going to divide by the same darn thing. So this is going to be equal to u to the negative 1 divided by negative 1 plus c. And I'm not all done because nobody cared about u. I know that's so rude to say. Everyone cares about your x. And so we have to go back to x, right? Because we have an indefinite integral, and so we need to go back to x, and we need to put plus c. And so x was equal to tangent of x. U was equal to tangent of x. I want to put that negative 1 out to the side. It's really driving me crazy. Negative 1, and then this is going to be tangent of x raised to the negative 1 plus c. And then I don't know if you all remember, if you all know, but that's, tangent of x raised to the negative 1 means 1 divided by tangent of x. So this is equal to negative 1, and then this would be 1 over tangent of x, right? If I did my my little rules of exponents, and then 1 divided by tangent of x is cotangent of x. So this is negative 1 times cotangent of x plus c. And I do get the same answer on that. A lot of times I'm asked, well, could I have left my answer right there? And would that have been okay? Yeah. Well, what about this? Would that have been okay? Yeah. But I kept going because I wanted to show that they were the same. And they were. Okay, so that was problem 24 out of your book. I wonder what they put in the back of the book on that. What did they put on the answer guide for that as the answer? I bet they put this, and I bet you the method that they show is this. But if they would have done this problem in 4.4, this is what they would have done, right? And so there's more than one way of going on it. Whichever way you see, sometimes I try to do a trig substitution, it just doesn't work. And sometimes I try to do a u substitution, it just doesn't work. This one worked either way. And so, you might say that this one was shorter, and maybe it was shorter. I think I wrote bigger here, and I also think I showed every step, and I also think that I got crazy in writing kind of big there. Okay, so I'm looking at this problem right here, and it's a product. And I'm like, darn it, I can't multiply that together. So I have to let my u be the inside function, and there might feel like there's two inside functions to you. There might feel like there's an inside function right here because of the raised to the second of x. And so I get people telling me u equals x, and I'm just going to tell you right now that the idea is to let u be something more complicated than just x, and it doesn't help at all to let it just be x. And so there is another inside function, and that other inside function is 2 plus x. And not that that's that complicated, but that's what you want to let your u be. So then du would equal dx, and I'm like, darn it, because what I was hoping for is that that part right there would become a u, and then that part would get gobbled up. And you notice it didn't get gobbled up. And so I'm like, oh, is it that double sub thing again? And that at least how he calls it. And the answer is, yeah, you could do that, because you could solve that. You could take this, and you could say this is u minus 2 equals x, so that u minus 2 squared equals x squared. I squared both sides because that was x squared. And then when I come up here and I plug all this stuff in, for x squared, I'm going to put in u minus 2 squared. For u, I'm going to put 2 plus x. And for dux, I'm going to put du. And so I have all these things to substitute in. I know that I'm going to have to put plus c, and I'm feeling like I might forget my plus c, so I'm going to put it down there, right there, so I don't forget. So this is, so that was u minus 2 squared, and then this was the square root of u, and then this was du. And so you might be saying, you didn't make it better, but I did. And how I made it better was underneath my square root, I had a binomial. And I don't know if you guys know this, but size matters. And so now underneath my square root, I have a monomial. And that means that I can distribute that, is what it means. It means I can multiply it. And actually, they've had us do this problem a number of times. This right here, you would use FOIL and multiply that all together. You put that square root of u, because it's a monomial in the front, and then you would FOIL that together. So that'd be u squared minus 2u minus 2u, right? I'm foiling it. You guys see me foiling it? I'm u minus 2 times u minus 2. What kind of u is that? I keep thinking he'll come in and tell me that the Angels have scored some runs and that I could quit making this video. U times u is u squared minus 2u minus 2u plus 4 du. And right there, that's like terms right there. So this is going to be u to the 1/2 times u squared minus 4u plus 4 du. See, I can multiply this together now. I couldn't multiply it together from the beginning. So after I did my u substitution, I can actually multiply this together. So this is u to the, what was that, 5/2 when I add those together, minus 4u to the 3/2 plus 4u to the 1/2 du. And if I didn't put parentheses around this, my office mate Dylan would go crazy. So he'd see that on the board. I'd be helping a student with a problem like this, and he'd say, "Ooh, are you missing some parentheses?" And I'm the parenthesis queen, and so I'm like, how could I miss any parentheses? So I've gotten in the habit of putting those parentheses in. The book always puts those parentheses in, and so I'm going to add 1 to the exponent. That's 7/2. So that's u to the 7/2. Divide by the same darn thing, so that's times 2/7. Minus 4, u to the 5/2 when I add 1 times 2/5, plus 4, u to the 3/2, add 1 times 2/3, and then plus c. And the only thing I have to do is clean up the 4 times 2. Was that a 2/3? That looks like a 2/5. Oh, it is a 2/5. Never mind. In my mind, it was a 2/3. The 2/3 came on the next one. Clean all of that up and substitute in back what x is, which is x is u. Substitute in for x, u equals 2 plus x, or x plus 2, either way. Doesn't matter. Okay, so this is going to be 2/7, and then I'm going to have 2 plus x minus 8/5 2 plus x to the 5/2 plus 8/3 2 plus x to the 3/2 plus c. If I take the derivative of that right there, I bet you that my algebra is not good enough to simplify it to that. And so I'm going to make sure my handwriting is a little better here. And I know I said what those numbers were, but when someone's looking at your numbers and not listening to what you're saying, and so if I wanted to take the derivative of this and show myself that it was that, probably what I would need to do is, because these were all like terms right in here, is I probably need to factor that. I mean, I probably need to whip out the F word and factor that. And then I probably could get back to where I started. It might be that when you look in the back of the book, they have factored that. This is number 30. They factored out a 2 plus x raised to the smallest one, which is 3/2, right there. Maybe they have. Maybe they haven't. I don't know. I have to admit I didn't look in the back of the book. I wish I would have. I might make a note to myself to go do that right now or sometime or whenever. I don't know. I'm pretty tired. I've had too much today. Getting to go in the snow, the Angels losing. Maybe they'll win. I don't know. My friend texting me that he's tired, grumpy, and has a headache. And I'm thinking, you think you're grumpy? You don't have your Angels losing because he's not an Angel fan. Okay, even functions. This is just one more thing. And remember the definition of even functions, we learned that in chapter 1, was that if f at negative x equaled f at x for all values of x, then it's an even function. And if you're finding the integral from negative a to a, and I'm just going to put on here where negative a is arbitrarily, and then come over here where a would be arbitrarily the same distance, right? And if I'm looking at an even function, that means it's symmetric through the y-axis. And I don't know if you all are noticing, but that would mean that if you looked at this side, that the area, net area, is just double the whole thing, right? And so whichever side you look at. So what they say is that you can do the 2 times and then go from 0 to a, from the center right here, the center, to a instead of your function. Now, why is that helpful? You might be thinking that's not helpful at all. But the reason that's helpful is because where people usually lose it is on arithmetic. And so that's when you plug in your bounds, and it's a heck of a lot easier to plug in 0 as one of your bounds than it is negative a. Actually, people make mistakes on negatives all the time because people are lazy and don't use parentheses. And so, anyway, and it's really helpful on odd functions. Remember what an odd function is. Odd functions are symmetric through the origin. And the reason it's helpful if you notice that something is an odd function, so I'm just going to pick out a negative a here and an a on the other side. It should be the same distance. And just so that you can kind of see, if this is an odd function, this is an example of an odd function. But do you notice that we have the same amount of area above the x-axis as we would have below the x-axis if it was an odd function, and therefore the integral would be 0. And if we were going from negative a to a, if we were going symmetric like that. And so anyway, they have a few problems in your book that without noticing that they're odd functions or even functions, can't solve them. And so, but you do have to have your bounds have to be negative a to a. In this case, I have negative 1/4, negative pi over 4 to pi over 4. So just that my bounds are opposite like that. And I'm looking at this and I'm thinking, well, I don't know how to integrate that. You know, I could, if I try to use substitution, I don't seem to have an inside function because x is not an inside function, right? Here I have x here, here, inside the tangent I have x. So it's like I don't really seem to have that. And so I have that product. I can certainly find the antiderivative of x to the third. But this part here, that's a product, and I can't do a u substitution to help myself because I really don't have a complicated inside function. You'd have to, in order to do this without using the fact that this is an odd function. So one thing that they're telling us right here is y equals x to an odd is an odd function. So this actually is odd right there. This is even because it's raised to an even power. But tangent is an odd function. And I don't know if you guys remember, but in chapter 1, you proved that an even function times an odd function is a, do you know what kind of function? Yeah, the whole thing together, all the way together, is an odd function. And that was one of the things that we proved in chapter 1, was that if you have an even function times an odd function, you get an odd function. So basically, I have the integral of an odd function from here to here, and an odd function, this odd function here as well. So this is 0 for this one, and this is 0 for this one. So this answer is 0. I know, it's pretty wackadoodle. And on that, and I hope that's it. I think it is it. It's almost it. I want it to be it. Could be it. I'm going to go watch the baseball game. I don't know if I should watch it. But just to summarize, because this is the end of chapter 4, we did integrals where you can just use the basic power rule. On this one, you had to multiply by the square root. Then you could just do the add 1 to the exponent and divide by the same darn thing. Because this is going to be a sum of 3 things, or could be a difference as well, then you're using that rule that you take the antiderivative of each piece and sum them. And also you have the constant multiples, the 3 and the 2. And then this is just a basic trig one. That's just one of our friends right there. And so we could just look that one up, right? And of course, you'll have those memorized, and you need to have them memorized. But I want to show you it. And so it's just a basic trig one. Right there. Cosecant times x times cotangent x dx is equal, the integral of it is equal to negative cosecant x plus c. Right, so that one, oh, that one's hot diggity dog. So there we have that one. This one, we solved this one. All of these we solved in notes, and we did, this one we used geometry and used area to solve it. Is this the one we solved, or did we solve a different one? I think that I forgot to change this to the one because they changed the problem in the book. And now that I'm looking at that, try solving that one and see what you got. But I know we solved this one, and we just did this one in the u substitution, and we just did this even and odd one. And so I say to you, good news. You will learn many, many, many more integration techniques in Calc 2. You will learn 8 new integration techniques. So these are the integration techniques that we learn in Calc 1. Some of them are basic and some of them are a little harder. The u substitution, the trig substitution, a little harder, or whatever have you. But you're going to learn 8 more. These come up all the time too. And you will smile when it's just one of these above types, is what I say, because you'll be like, oh, hot diggity dog. I'm so grateful. Okay, so I think that we have ice cream here, and so that will at least make the baseball game feel better. And so I think that I can upload this to YouTube.